As always, there have been very good questions in the break. The first question was, now, what we've been discussing training of perceptrons. But then at test time, what does it actually look like? So indeed, all of what has been discussed here and all of the equations, this was for train time. And training here meant that we minimize this loss surface over the parameters to find the best set of parameters. So what happens at test time? Now I have found some parameters, and now I want to have some kind of prediction. Yeah? So let's say we have a prediction. I'm calling it f of x. Now given these parameters that I have learned, and the prediction for the perceptron here would always be +1 for the one side and -1 for the other side. Yeah? So I can write this, for example, as twice the Heaviside step function of xi transpose w. Now I don't multiply with y because that's what I want to find out. -1. Yeah, so I get +1 on the one side of the decision boundary and -1 on the other side of the decision boundary. The other question was, we were discussing these loss functions here in general. And by the way, this picture of these so-called surrogate loss functions that we see in this plot here, surrogate loss functions. A surrogate in German is Ersatz. In this case, it's Ersatz for the one that we would really actually like to use, the Heaviside, but it's too difficult to optimize over. So we need an Ersatz, we need a surrogate. And that this fact that really whenever we use something convex here, that this will give us overall a convex method. And the particular question was, let me take green here. The particular question was, well, what about the parabola? So if I use this parabola would mean that preferably for everything on the right-hand side, I want to predict a +1, and preferably for everything on the negative side, I want to predict a -1, and then I give a quadratic penalty for deviations from that. And the model that this particular surrogate loss function translates to is just linear regression. And I try to draw a picture here on the right-hand side where now for the training set, I've drawn on two different planes, on the plane of -1 and of +1. For the two classes, +1 and -1, where are my training examples? Those are the dots that you saw here. And then I try to draw or fit a surface to it, just as we did in linear regression. And this would also give me, some kind of perceptron, because now I can intersect this plane that I fitted here. So I fitted this plane here, and now I can intersect it with y = 0. And that will also give me a decision boundary, which maybe in this plane looks, I'm not sure, something like that. And that would also discriminate the two sets of points. It's just that this quadratic loss is a weird one for a classification problem. Yeah? Because, and that was the sketch up here, let's say even if I have a one-dimensional problem, and even if my data set is perfectly linearly separable, then my quadratic loss will still give me these loss contributions here, which we can imagine as springs because it's a harmonic potential. Yeah, so I still get these springs. I still get this tension in my system, even though the two classes are linearly separable. And hence, it would be much nicer to use a system such as this, which is what you were discussing last week, logistic regression. And then I can ask again, okay, and what does logistic regression look like in terms of the surrogate loss here? Well, it looks like this, and it has all the good properties, except, unfortunately, it's not convex. So we're back to this problem of local optima and such. And well, this fact that neural networks have all these local optima that was long thought to be a bane of the method. So this is why theoretically minded people didn't like it. And this is why everybody loved support vector machines and why everybody used that for 20 years. Until it turned out that empirically, in spite of these local optima, just given enough training data, given big enough GPUs, neural networks in the end, will win any time. Yeah, and that's why we're doing neural networks. Except this perceptron, a multi-layer perceptron, I've been teaching even during the last neural network winter, because conceptually, it's this idea of mapping to higher dimensional space is super important. It has always been valid, no matter whether optimization has been difficult or hard. And that's what I want to talk about now. Yeah? So how to stack perceptrons into nonlinear classifiers and what this means conceptually in terms of mapping to higher dimensional spaces and such. So the multi-layer perceptron or feed-forward neural network or artificial neural network or known under many other names. This picture, again, is in the public document. This is the very same training set that you've seen above. And you also see two perceptrons here, A and B, that do something useful, the green and the black one, but neither of them are really sufficient to do the job all the way. However, if we now use, let's say, logistic regression for each of them, so what does that mean? Let's say for the black one, this means we're going to predict 0 here, and we're going to predict whatever, 0.2 there, and .5 here, and then 0.9 there, etc. And then on the other side, we will have minus 0.2 here, and minus 0.5 there, etc. So we have a sigmoid. Yeah? And what you see in black here at the 0 line, this is where the sigmoid, well, has its inflection point. Let's use this sigmoid and get a prediction for each observation. And this prediction here for the black sigmoid I've called phi A. And it gives us a new set of coordinates. And we can similarly, I need to clean up this plot again, I can similarly do something for the green perceptron here. Let's say this is the green perceptron. And now imagine a sigmoid which has its inflection point right at this line. And it gives us positive values on this side and negative values on the other side. And let's call this prediction phi of B. So that means now for each observation in my training set, for each original observation, I now get two predictions, phi A and phi B, and they are collected in this plot here. And in this plot, I have retained the color coding. So in this plot, the blue examples, the blue class, it got a large value from the one perceptron, it got a large value from the other perceptron. So this is where they ended up. The negative ones you see here spread around feature space elsewhere. And now in this new feature space that we've just constructed, I can now find a perceptron which will actually separate the classes. I can give it a normal vector and fit a perceptron here, which I'm going to call phi C. And I can thus append it. Yeah, so that means a combination of three perceptrons in this case is actually able to perfectly fit my data. Now there are more examples here for different so-called activation functions or different predictions that the individual perceptrons are making. Let's maybe start with the one on the rightmost side. So for this plot here, I have simply, as activation function or as prediction, I've really used a Heaviside step function. So each sample gets a +1 from, this is perceptron phi A. Each sample gets a +1 if it lies in this half space. How do I do that? Okay, I get a +1 here, +1 there, -1 and -1 from the first perceptron. I'm not still happy with this plot. Let me make one more try. I'm considering the black boundary, yeah? And I'm saying whatever lies in the direction in which the normal vector is pointing gets a +1, and whatever lies on the other side gets a -1. And now similarly for the green one, whatever lies in the direction of the green normal vector gets a +1, and whatever lies in the opposite direction gets a -1. Now I have two predictions for each of my observations, namely in this set here, I will get +1, +1. And of course, the perceptrons have been judiciously chosen. So for all my blue training points, I get a new coordinate of +1, +1, meaning they end up here, +1, +1. The ones which are in this part of space, they are under the first perceptron and under the second perceptron, so they get a -1, -1. So these points are mapped here to -1, -1. Well, and there are these other two quadrants. Points here, they are above the black perceptron, they get a +1, but they are in the, if I consider the normal vector of the green perceptron here, they are on the other side of the green perceptron, so they get a -1. So they are mapped to +1, -1, which is this coordinate. And lastly, points down there get mapped to -1, +1. So they get mapped here. And if I zoom in, you see again the colors. So I have 3 red corners and 1 blue corner. I can again find one perceptron which will perfectly separate my classes here. So this is where, as activation function or as prediction for my perceptron, I used a step function. Then, so we've discussed the two rightmost plots. Let's look at this plot here. Here I've used a mild step function. Okay, cleaning up. This was the green one. This was the black one. I've used a mild step function, and in my plot on the very left-hand side, this is something interesting, I think. So here, the activation functions were both linear. So in other words, this phi A is some affine combination of my original coordinate axis, and phi B is an affine combination of my original coordinate axes. What does that mean for this point cloud relative to my original training set?
I think you can transform it with rotation and stretching, so you get the original set. Meaning that if we only have linear functions, we will resolve in a linear function.
Exactly.
Doesn't change anything.
Yeah. So because phi A is an affine combination of my original features and phi B is an affine combination of my original features, this entire training set here is just a somehow stretched, possibly flipped version of my original data. And if we really look closely, I think we would be able to figure out. So let's say if I'm calling this point here 1 and this 2, then I think we have 1 and 2 here. And if I'm calling this here, I don't know, G, then and H, then I'm guessing that maybe one of them will be H and one of them will be G. You figure it out. Okay. All right. So it's just we've somehow linearly transformed our original data, and now let's look at can we fit a perfect decision boundary here? Well, no, we can't. Huh? So we could not in the original features, and we cannot in the new features. And this is a very fundamental insight, that here on the right-hand side of this plot, somehow, magically, a perfect separation became possible. So it was possible here, it was possible there. It might even still be possible here. So I might even still find a decision boundary that works there. But it was not possible on the left-hand side. And if we look again at what are the activation functions, what are the transformations of my individual perceptrons, these here have been nonlinear, whereas the one on the left was just linear. And that makes for a really qualitative difference. So after these nonlinear transformations, perfect fit to my training data becomes possible. Whereas it was not possible for the purely linear transformation. Okay, and there is a deep reason for this. So this is something which is called the projection trick, namely that nonlinear mapping to a space, preferably to a higher dimensional space, makes linear separation possible. Yes?
You would assume that a perfect fit is possible in the end. But do we also have the possibility to add a stopping condition or something?
Add a what condition, please?
A stopping condition. So if we do not want the perceptron to have, I don't know, thousands of layers, then it somehow needs to stop, even if the training is not perfect.
Mm-hmm. So the question was, do I really want to have a perfect fit? And you raise this issue of overfitting to data. Yeah? And that is, of course, a valid point. If my training data is small, then I need to be very cautious with overfitting. If my training data is industrial size, so I have tens of thousands of annotated images, and I have very deep neural networks with millions of parameters, then a typical strategy is to first really try and overfit the data, so try and get a perfect fit to make sure that the neural network has enough capacity, sort of to learn everything by heart, just to be on the safe side capacity-wise, and to then start regularizing to make sure that, well, you are not going to overfit at test time. And as always, something like cross-validation can be helpful in then deciding how strongly you do want to regularize. But for now, I just want to make the point that yes, I want to be able to perfectly fit my data in the first place. Yeah, which with just linear regression or with just logistic regression is not always possible. All right. Now, if you ask me, for this specific training data, what classifier would you actually use? For this specific training data, I would actually just use logistic regression and nothing more, because I have so few training examples. This is now just a sketch for, assuming you have much, much more training data, and even then it's not linearly separable, what do you want to do next? And for real-world decision problems, it does turn out to be necessary to use nonlinear classifiers, such as neural networks, to do better than what you would get with logistic regression. Yes?
What happens if I also have one blue point at the left bottom corner?
What happens if I have one blue point also in the left bottom corner? Very, very.
Yes.
Okay. You mean in the original training data?
No.
Yeah. I mean, then of course, then I cannot perfectly fit in this example then I cannot perfectly fit with this particular construction, this particular training set. Yes. Mm-hmm. Yes.
Do we limit ourselves with the kind of maps we use? Because you said they're just non-linear, but I mean, there are probably for example, you can use affine maps, or is the only restriction that they have to be maps so that they have to be objective?
So they have to be. The question was these maps or these activation functions. What should they look like? Now they must be nonlinear for my system to exhibit interesting properties. But then secondly, the question is how hard is optimization of the entire thing going to be? And if I use this map here, the Heaviside step function, then it's going to be very difficult to find good parameters because my loss surface is piecewise constant and I don't know how I should change the parameters of my perceptrons in this first layer in order to get a useful intermediate representation. So in practice, I want something, I'm going to look at the final result and then I'm going to try and differentiate this final result with respect to all of the parameters in order to see, or I'm trying to differentiate the error that I find with respect to all of these parameters to see how should I change the parameters. So it means I want to get useful gradient out. And for this Heaviside activation function, I get no gradient at all. If instead I have a pretty steep sigmoid, then it's still difficult to get useful gradient in this part where it's saturated. So in practice, there is a huge difference in how well these methods will work depending on how easily you can propagate information through especially deep networks. And your question is a very good one because in this previous, there have been these cycles of how popular have neural networks been. And in the previous cycle, people were using sigmoids, so they were using logistic regression perceptron throughout because logistic regression is so well understood theoretically and so on. And then it turned out that empirically, because of these effects of saturation and so on, it turned out to be better to use much simpler linearities. In particular, what people actually use nowadays are variations on the theme of hinge functions, which in this field they don't call hinge functions, but they call rectified linear units. They are, as you can see, nonlinear, and yet they give. We had this point raised earlier about getting informative gradient, no matter how far you are, at least on the one side, and they turn out to be a very good compromise. And then a zillion papers have been written. If it's not better to, rather than have it go to zero, if it's not better to have it go, maybe with a little bit of a slope on the other side, that would be then called a leaky rectifying linear unit. Or you can say, all right, I don't like this kink here. Why don't we make it a little bit smooth here? Make it zero there, make it linear there, but in between we want a little bit of smoothness. That would be called an exponential linear unit. And whatever function you can come up with that is nonlinear and that somehow is linear as you go further and further away. There was a point in time when whatever function you could draw, you could write a paper about. Some people did. Not that it's the kind of sport that I enjoy, but yeah. So there has been a huge body of experimental work on what are good activation functions. And these rectifying linear units have turned out to be good compromise. Yes?
If you could again explain how you choose your WA and your WB.
How?
Because, okay, now you can see when you separate them like this, you would see that in one fragment you have all the blue points, right?
Yes. Excellent question. Yeah. So I will give you more details on Wednesday. Yeah. But what we get out, if we look at this diagram, yeah, then we have some inputs here, x1, x2, and the constant here is just so I can work in homogeneous coordinates, and then I get some output here, f of x. Now I will compare in a loss function my output f of x with the true class label that I know from ground truth. So let's say I have a label yi for my ith training example, and I have my prediction f of xi. By the way, my notation here is not super consistent, because when I here say x subscript 1, I mean the first dimension of a particular observation, and when I say xi, I mean the ith observation. Okay. So now I can sum this over all observations. This is a loss function. Now, my prediction of the neural network depends on the parameters WA, WB, WC. I write in short, it depends on all the parameters W. So this entire thing here, for a given training set, gives me some kind of loss, which I can call a function epsilon of W. And now you ask, but what W are the good ones? And what we do at train time is, on abstract level, I'm just writing now, I'm minimizing this epsilon of W over W. Now, of course, this does not say how do I do it. In practice, we do it by some version of gradient descent. And more on that, more details on Wednesday. Okay? All right. So for now, let's say what we have just done here. This kind of thing is called a multi-layer perceptron, or MLP for short. It combines several perceptrons to altogether create some nonlinear decision boundary. And what we've seen is that these internal perceptrons they map the data to a new feature space, and this mapping here should be nonlinear to do anything interesting. Because if it is linear, then yeah, it's just an affine distortion of our data. And just, you know, I've made this kind of sketch above. Nowadays, these sketches in deep neural networks are obsolete because we would have to draw millions of these. But at the time when these perceptrons and multilayer perceptrons were developed, and they were invented several times, but also by electrical engineers, and this is why we have this electrical engineering kind of diagram, would look like that. We would have some input, let's say x1 tilde, and this input would be weighted with a weight w1 tilde. And then we would have a so-called bias. And this, well, the sigma in the middle is meant to be a sum. Yeah? So this is a summation unit. And what comes out of the summation unit here would just be W transpose X. But now we need to make some kind of prediction with each perceptron, and that happens by means of this activation function. Activation function, or in the more modern literature, this is called the nonlinearity. And, well, you know, indicated in this box is schematically that in the earlier days people would use a sigmoid here. Nowadays they would use a rectifying linear unit. And then this result here would be, let's call it, or earlier I called it phi of x given some parameters. Okay. So we've seen so far by means of a specific example that given specific parameters that work well, I will be able to have something that fits my training data. On Wednesday, I will give you constructive proof that if you take sufficiently many perceptrons, we are able to fit no matter what. So I can fit whatever training data I want perfectly. And I will give you, in terms of the function counting theorem, an argument, a more quantitative argument, why this mapping to a higher dimensional space helps. And then we will also start looking at this question of gradient descent, which in this field is called backpropagation, so how to actually find the good parameters. Today we finish on time. Thank you.